Hi, Markus.
Markus.
You're live. You're live, and audience, please join.
Copy. I don't know if that's me or if that's you. This is your connection or mine.
I hear myself well, and you.
Okay.
I hear you well also. Please, everyone, join Zoom.
Okay, I'm in the dark here. I don't know where I should start or not.
Markus,
don't have the tech talking to me.
Okay, while Markus is trying to fix we are trying to fix Markus' technical issues. Markus, can you hear me? Guys and everyone, please join the Zoom session.
He's trying to talk to you, Markus.
Okay, Markus?
He's trying to talk to me. That's great. I can't see him. So hello, everybody, I guess. So this is one directional communication, distributed systems failing, I guess. Can't answer any kind of questions, but I'm happy to be back. I see that people are joining the Zoom call. I think we will do that right now. So if you want to join the second installment or the second part of the TLA Plus tutorial, please go and join the Zoom call again, like yesterday. We're going to continue from where we left off and try to make our termination detection algorithm really work under the assumptions that we made and learn TLA Plus in the process, right? To quickly recap, and I hope that I'm allowed to jump right in now and talk about yesterday's content and today's content. So yesterday as I said, we climbed Mount TLA, and from here on it's downhill. So we really covered the tough parts, and I hope everybody can see my screen. If you don't, then give me a sign. We learned everything about the temporal parts of TLA+. This obviously takes some practice. I don't expect you now to just yank out these formulas in no time. This requires some internalization. But the learning material is here, and if you follow up offline, you will probably figure it out and can get proficient in TLA+. What I skipped yesterday, what I didn't get to were a couple of commits here towards the end. The proof type OK, user Palachi, the symbolic model checker I've mentioned a couple of times, to get some stronger confidence into the proof before I do the proof. And I will defer this further. I won't do this today. I don't think it's like opening a different book. So let's not do this. Let's focus on the other stuff that's more relevant to the actual modeling in TLA+. If there are enough people who reach out to me after this talk, after today, and request to see the proof system, I guess if there are more than 3 people who reached out to me after today to show the proof system, I will record some bonus material and perhaps even get Stefan Mertz, who is one of the primary authors of TLabs, to join me or to do the recording. So today I want to continue at the interlude here, what's called the interlude. Where are we? So to quickly recap what we did yesterday, what we learned yesterday. So we wrote this ultra high level specification of async termination detection. I generated this PDF from a trimmed version. So I removed all the comments, and you really see what we did fits on 2 pieces of paper. And this is all there is. The temporal formula that defines the specification, init, and always a next state and some weak fairness over next. Terminated leads to termination detection. The spec is also stable, and we have those 2 theorems here. We have our next state relation. We have a bunch of actions: detect termination, wake up, send message, terminate. we've seen infinite sets of functions, infinite sets of functions, finite sets of functions, or the expressiveness, how to check invariance with type OK, that you can prime operators, and so on and so on. So almost all of TLA plus, I guess 80% of TLA plus, or the other way around. We've seen perhaps 20, 30% of TLA plus that let you do 80% of what's interesting. Now we want to apply this and go to EWD 998, learn a few missing concepts, I would say, that should be in the beginner's tool belt of a TLA plus beginner. If then else, I think we mentioned it yesterday, it's no big deal. Recursive functions, recursive operators, what are those? Sometimes it's useful to use recursion, tuples and sequences. If we need order for some reason, because sets don't have order, there is no order. This choose operator, otherwise called Hilbert's epsilon, that appears in some specification. And then the big thing I've been building up to is refinement, which I believe and others believe is the underappreciated beauty of TLA plus. So this is what we're going to cover in terms of the language. What we want to do in terms of termination detection is now really at this this token thing. This token here represents the token that's going to travel around the ring. Yeah. Yesterday we just counted the messages. Today we're going to model the token passing. You are going to model the token passing, and I will just do the typing so that you get a sense of how it feels to model with TLA plus. And the informal protocol I gave yesterday with the animations is fortunately also written down, has been written down by Dijkstra many years ago, as I said, in EWD 998. And I will just open this paper because I find this paper so beautiful. PDF viewer always needs a kick. Okay, because this is here obviously a paper that predates LaTeX, right? It's handwritten, but it's a great paper, and I highly encourage you to read it just for its beauty. I don't know how people can write this nicely, and it's also formal. And Dijkstra and Safra, they give a number of rules here. Rules 0 to 6, I believe, so 7 rules in total. I've extracted those rules into EWD 998. Here I've slightly reordered them and massaged the terminology so it better fits with what we did yesterday. And this now really describes how this token passing works. So rule number 0, some node I, if it sends a message, it increments a counter. If it receives a message, it decrements the counter. So now locally at each node, we have a counter that counts the outgoing messages and the incoming messages by incrementing, decrementing this counter. Receiving a message by some node, not the token, a message, blackens the receiver node. So I get a message, I become tainted, I become black. An active node J, who happens to have this token, right? So I'm the owner of the token right now, keeps the token. When I become an active as this node, then I pass the token to my neighbor. And on this token, I write, okay, my current value of the counter is so and so. And because the previous guy also wrote this on the token, we just do a sum of the previous counters and mine. A black node taints the token. So if I'm happen to be black, well, then this token also becomes black. I have black hands, the token becomes black if you want. Think like that. But once I pass on the token, I get white. So my stain gets transferred onto the token, and afterwards I'm pristine again. And then the last 3 rules are related to the initiator. The initiator sends a new token around the ring. The token is new, it's white. The counter on the token, the Q, is 0. The initiator keeps sending tokens around the ring until there's a conclusive round. And the initiator whitens itself, and this is kind of a little bit redundant to rule number 7. When it starts a new round, it also whitens itself. Okay, and now the question is, how do we translate this into EWD 998? Do we start from scratch? We could, but I say let's use what we did yesterday. And by the way, if you want to follow along now, you can see the git commit ID down here at the bottom. So I essentially just copied our async termination detection spec into this module here, into EWD 998, and everything should look familiar, perhaps, except for these two strange annotations here that we're going to skip. And I made one minor modification. I separated the spec into what I call the system and into what I call the environment. The environment are the actions send message, receive message, deactivate. So what this termination does, that for which we want to detect the termination, and the system is really just the part where we do the token passing. That's related to the token passing. Okay, and now first question related to modeling. What kind of variables do we need in addition to the existing ones, active and pending from the old specification? What kind of variables do you want to add to this specification? And somebody please speak up.
Okay, I think this must be the number of node where token is. So maybe token position and token state, which is a number attached to token, and it's white and black state.
Okay,
and we also need a function for node state. So they should be white and black.
Okay,
also.
Yeah. I propose we call this color, I guess, and token. Is there more? So I see this color is kind of implicit here if you read the text, right? Blackens, whitens. This indicates there is some state, some color. We have the token, obviously, and then we have, I think, one more variable here, which is the counter, right? Pending is the message is pending at the receiver end. This is what we will use to check our algorithm. The counter is at the current node that sends and receives messages to keep track of how many messages it has going. So we need also a counter down here. So I would say probably that counter looks like this active here, this pending here, right? So pending is almost verbatim to. Sorry, it should have been counter, right? Not active again. This is our counter. Can somebody quickly say what the type OK should look like for counter?
Like for pending, I think it's natural number for each.
For counter, please. For counter.
For counter, yes, like for pending.
Like for pending, okay.
In a set of functions from node to node.
From node to node. Okay, so the counter counts the incoming and outgoing messages. What happens if I receive more messages than I send?
This shouldn't happen. Should we assert this in type OK?
Why shouldn't it happen? Why isn't it possible for the environment to send for some other nodes? So it could be in our computation where we have 8 nodes that 7 nodes send some result to one specific node. I'm not talking about the initiator here, but one node is simply the node that collects the result of the computation. Then this guy or the skull receives 7 messages, I would say, without ever sending a message. So that's fine, that's okay. which suggests that this has to become int now, right? So this can become negative. We would have found this later, I guess, and then the type OK would have been violated. So color, once again, I would say that's probably best modeled by this function here from domain node to some color. And initially, we mark them white, perhaps. What would init look like if we would want them non-deterministically be black or white? Could somebody just spell it out to me?
I think we should choose the arrow. Oh, no. It should be not equal, but should be in the set of functions from node to color. Yeah, color should be in the set of functions from node to color.
Yeah, and then this just gives us one function, right? This arrow here just gives us one specific function. So we want to use the syntax that we also have for active and make this right-hand side here the set.
I think we can write color here. Just we define.
Oh yeah, right. I wasn't sure if it was in this commit or the next. Mm-hmm. Okay, so now the color of the nodes is non-deterministically chosen to be black and white. And what's left to be done is, what does the token look like? Any suggestions how we would model the token?
It should be 0.
So again, if
we should. What is it? I think token is just a natural number which represents at which node the token is, and
okay, so
let the leader be zero node. Okay.
Fair enough. I think that's a great agreement. The leader or the initiator is at 0, is node number 0. But if we go back to the modeling and think about this and read it, passes the token to its neighbor with q equals q plus counter j. So we have some state on the token. And there's a second state for the token, which says token can become black or white. So we have this thing that we pass around the ring. So the token must be a function, somebody says. Okay, what kind of function? Obviously, I want to get at something, to learn something new in TLA+, which for some reason wasn't on my list, to-do list up there. Anyway, so we can define functions. We could probably come up with some mapping from node to, and then some other function perhaps, and then to track where the token is, we move the token inside of this node to token mapping. And for the tokens where the token is not, there's some null value or something like that, right? Which perhaps you would have done in programming language or so. But there's this other type of functions, which are called records, where we can have keys here. And the key is just a string, but you can omit the quotes. And then we say the position of the token initially is at 0. The Q value initially is 0, and the color perhaps of the token initially is, what should the color initially be, black or white?
White according to specification, if I'm not mistaken.
We're here to make mistakes, right? We learn from mistakes. I don't think it's said here explicitly what color the token should be initially. But let's go with white and see what happens. But really what we've done here is we use just additional syntactic sugar to define a function that we call record, where we have keys in the domain. So this is, the pos is a key, the Q is a key, and the color is a key. If we would want to access a value here, we would right? POS, right? That would give me the POS. Or there's another shorthand that I can type just this here, .pos. Then I would get the value of the POS. Okay, let's try and write the type OK, right? We always should write a type OK. What kind of function this is here? Anybody happen to know the additional syntax that's available? I guess not. I haven't introduced it yet, right? So you can't know. There's this other variant of writing a set of, so we again define a set of functions, which are records. So instead of this arrow here, I just use the colon and then give it a set on the right-hand side. So this is node, right? The position is always some node. Token cannot get lost, if you will. The Q is in integer, I guess, because of counter. Yeah, I guess it could be negative. And the color here happens to be the color from the set color that we've defined up here. So this now gives us the set of records that define the concrete value of the record here for token. So this is how you would usually translate something like a prose document here into variables, right? I went to look for counter, black and white, so color, red color out of it, and the token itself. So what's left now for us to do is define the system, what the token passing looks like, and the rest of the actions, update the rest of the actions. I'm going to skip forward again a few commits. Let's see. So we've done token. Here's the to-do for the learning material, offline learning material for the records. You can play with records. And perhaps let's just quickly start the REPL. So this is a record here. I hope copy paste works, yeah, right? So this gives me the 42. This is also the syntax here. And this now here is the set of records. How many, what's the cardinality of the set here? How many records are we?
Nine.
I guess so. Cardinality. Yeah, 9, right? So we get it. Let's see, I guess this is short enough for TLC to print. We get an A1, B4, A1, B5, and all the combinations, right? Okay, so much for records. Now what's is left to do for us in terms of modeling? For some reason, init is not done yet, so I guess I want to move ahead one commit more. And I believe you wanted to have the token initially white. Okay, but let's now do the initiate probe action here. I said it's rule 1, 5, and 6 that's relevant for the initiate probe. I won't be able to have them both on the same screen, but I guess you on your computer can just have the rules in front of you if you need to. And maybe somebody else can now spell out or help me do the initiate probe action. What should it be? No, don't be shy. We're all friends here.
I don't understand the question. We already have initial step, and what should we do next? The next step?
The question is not the init predicate, but the initiate probe action. So the initiator sends the token around the ring. This action is what we want to model now.
Initiate probe. Okay.
So, and it's rule number 1, 5, and 6. So it's the initiator sends the token with a counter Q initialized to 0 and color white. The initiator starts a new round if and only if the current round is inconclusive, for some informal definition of inconclusive, and the initiator widens itself and the token when initiating a new round. So
okay. We should modify token variable. I see. We should modify token variable here.
I will move this stuff down here so that we can see it all at once.
Yeah. So, so this must be token
I will do
prime.
the color part. Okay, I will start with the color first because that we've seen before, right? So this is accept node number 0 is equal to white. We've done this so many times yesterday. The color was easy. Okay, you were saying.
Yes, now we're modifying token prime.
Okay.
Prime equals, and I think we can rewrite the whole record here. Pause equals to 1, or maybe a pause to pause plus 1. I'm not sure.
Yeah. I guess it's up to us if we send the token clockwise or counterclockwise around the ring, right? That's a modeling decision.
I think that if clause should be here. If we reached the maximum number, we should return to 0.
Okay, I like that. So Q, I think is 0, and then the color is white. Okay.
And what is N?
And what else? N is the number of nodes, right? So N minus 1 gives us the N minus 1's node.
I see. Yeah, okay. This should work.
Okay, and now I think we're pretty much done with rule number 1 and 6, but we still have to do rule number 5.
That's if the current round is inconclusive.
What does it mean to be inconclusive?
If the color of the token is white.
Okay, so token color is equals white.
And its position is 0, maybe.
Token pass equals 0. Yeah, and I think there are a few more, and we could perhaps look at. Yeah, we have to think about this. I would say, I guess we would also have to look at the counter of the 0th node of the initiator, right? If it has messages pending, then it cannot send a new round, cannot start a new round. And also, if the initiator is black, well, then it can start a round. But its counter, I guess, is something we would have to account for. But let's see what I came up with in the. And I guess I have to undo or save this here. Cancel, save, overwrite. Okay, so this is what I came up with in the git commit. So the token has to be at position 0. In the previous round is inconclusive, so the token color is black. The color of the initiator is black, and the counter of the initiator plus the token counter is greater than 0. Okay, great. One action down, I think one more to go. So who wants to do the next action? The pass token action. And I'm going to copy, 2, 4, and 7 down here so that you can see it. 2, 4, and 7.
Folks, maybe someone else will try. Because I'm the only person who speaks here.
Yeah, don't be shy. Everybody else, don't be shy. You can also type into the chat if you want, but just try. And you can also cheat, right? You can just jump to the next commit and read out what's there, but there's really no reason. We're here for the learning. So somebody? Perhaps Paulo?
Let me
So let's start. Let's start with 7. Passing the token whitens the sender.
So you maybe token want to change the token prime?
No, we want to whiten the sender now. So
the sender
has
token,
token.
right?
Yeah. So I guess we can just copy paste the color from up here and then do the
NY.
I here. Okay. An active node J owning the token. So owning the token, that's important, right? So the token pos has to be equal I. That means that this guy owns the token. And when J becomes an active, oh, there's another thing here. Active I equals false, right? Or I will just use this here. This looks a bit nicer, more compact.
It passes the token to its.
It passes this token to its neighbor with Q equals Q plus counter J, and the black node taints the token. So we have to do something with the token, obviously. Token prime equals
Q.
Okay, so
Updated token.
Yeah, I do the pos here. So I guess that's I minus 1. The Q is, it's almost written verbatim up there. Copy paste it, right? I. So what happens to the...
sorry, isn't it token.q plus counter I?
Oh, right. Good catch. Good catch. Second pairs of eyes, always better. Okay, and now the black node taints the token, but only a black node taints the token. And this is obviously, right, an if, right? So if the color of this ith node is black, then black else token. The color of the token stays the same. Stays the same. Great. We won't need this anymore here. Do people want to do the send message, receive message, and deactivate, or is this too easy?
It's not easy at all. It's
well, this is the
practical part,
right?
Yes, the practice part.
This is the practice part, exactly. So I think, so this is going to introduce the if here. So this is written now like an if clause, and I think, okay, before we move on to the send message and receive message, I'm just going to show you a little bit of additional syntactic sugar. So this is essentially just the record we just defined. So it's token, but we can also use the accept syntax here, right? It's just a function again. We can do the accept. And then instead of writing this here, I can also write .q and .color and update multiple keys of this record at once. And I still, again, have this at here, right? So this is just a little bit syntactic sugar sprinkled on top of on the accept. And that really shows that records are just functions with a particular domain. Okay, so here is the counter for the send message. We increment the counter. We received a message, we increment the counter. We've done that yesterday. We know how this works. And then choose the recipient of the message. So we send a message to some node. And today it's different. Yesterday we had the I and a J here, right, in the send message. But today we don't. For some reason, I decided to let the send message decide where it wants to send the node. And that means that pending prime equals pending accept. yes, some value here, receiver, for which we are going to increment I, but we have to get the receiver here. How do we want to determine the receiver?
In a random number.
Random number, okay, random is interesting. That sounds pretty much like a random number generator. There happens to be a choose. That's an interesting thing. I mean, the chooser recipient hints at it, right? Quickly about the random number generator. So there happens to be a module randomization in the TLA plus standard modules, and sometimes they are useful, but usually not in the behavior part of the specification. They're very niche application. But let's go with choose. So there happens to be this choose operator in TLA plus, capital choose. Choose some n in some set. Yeah, this is obviously the set of nodes, and this n, I guess, shouldn't be equal to I. Choose some n in nodes such that n is not equal to I. Okay, so what does this choose look like? I think I have an explanation here. Sorry, pressing the wrong buttons. Here's my explanation of the choose. Choose is, and Andre, I'm going to address your comment in a minute. Choose selects an element from the set here that satisfies the P, the predicate here. And if I choose again, it will choose the same element. And no matter how many times I choose, I always get the same element. This is the semantics, these are the semantics of choose. So it's different from the exists, right? The exists will give you just, for TLA plus give you all of them, choose just gives you a single one. We can look at an interesting specification, I believe. I guess it perhaps comes in the next commit. So, okay, I have to move one commit forward again in hopes that we now, where is my C file? There's supposed to be a C file here. No, I don't remember where it is. So the choose, I have to do this in words, not with a file. The choose really is the function that always gives us the same value. Even if we would use choose in two separate actions and choose from the same set, we would be guaranteed to get the same value. And only this value. This is useful, and we can use it here, right? If you choose from an empty set, this is also not a runtime exception or anything in TLA plus. It just gives you an undefined value. You don't know what the value is, and it probably won't be able to compare this value to some other set that would make it a steady expression, but you really get something back. The tools, and there's sometimes a mismatch between what the tools do and what TLA plus does, because it's hard to implement TLA plus faithfully. The choose for TLC, when you choose from an empty set, it will really do a runtime exception and say, yeah, I can't do this. But in TLA plus, in the math, this is fine. And TLC also won't choose from an unbound infinite domain. So if we choose from the natural numbers, it will say, sorry, can't do that. So let's see. TLC REPL choose n in nut. And this won't even, attempt to compute the value of an expression, choose such, but S was not enumerable. Yeah, sorry, no can do.
And from Boolean, it will choose false, I believe.
It will choose false, right? And I guess it will probably always choose false. And there are a few corner cases with TLC that you need on the right-hand side, need the same expression, syntactically same expression. It's outlined in specified systems. But once again, I make deliberate mistakes. This is kind of an outlook into the future, and I'm spoiling the conclusion here, but this is going to be wrong. And this is what Andre said in the chat, why not there exists a J. We should write there exists a J here, but I will go with a choose for now to make this mistake and show you later what this will cause, what kind of problem this will create. Okay, I think we have the receive. The receive, I believe, is boring. Let's see. Yeah, it increments the counter of the receiver, decrements the counter of the receiver, and this rule number 3 that says the color flips to black for this node. Okay, what else? Okay, perfect. And I go one commit back, I believe. So we've learned about choose now, and I think we're pretty much done with the specification of EWD 998. We have our initiate probe, we have our pass token, which we call system. Haven't talked about this one. So this is what the system can do. It can either do an initiate probe, or it can pick a node, except for the 0th node, and pass a token. And then the environment down here either sends a message, receives a message, or deactivates. Deactivates used to be terminate, receive was wake up in the high-level spec. And this is what they do, right? Pretty straightforward. So we can model check this, check model with TLC. And for, I believe, 3 nodes, we have approximately 17,000 distinct states, a diameter of 37.
Sorry, can we have a look at spec formula?
Okay, yeah, spec is down here. This is part of a silly exercise. Spec is.
I see. Standard spec. Before. Yeah, I see.
No,
no fairness conditions.
No fairness yet. Mm-hmm. Why does it say success? Why is everything green?
Maybe because something's wrong with our spec.
We haven't checked anything about our spec, right? I think we might have checked type OK. I don't know. Let's look at the config file. Yeah, we checked invariant type OK. So apparently we made no mistake in type with our types. And I also set up a state constraint here once again, right? We've seen this yesterday to keep the model finite because we're using these counters here. And they could grow unbound. Okay, let's quickly go back. So I think initially we wanted to model the counter is not. I guess this should cause a problem now. Yeah, it does, right? So be suspicious of success. There's a counter here that goes -1 because this node number 1 received more messages than it sent. So this really has to be in here. And I think one thing I didn't reveal is what happens if we initiate the token to white. What would happen? I really haven't tried this out, but I believe that this would mean that we would immediately have a conclusive round, right? Because the token position is at 0, the Q is 0, the counter of the 0th node is 0, and the color of the token is white. So the initiator will just conclude there is global termination. So we have to color the token black and perhaps assign some value here in addition to be really safe. But we could have found out easily, right? Once we check the specification for some more useful properties. Can anybody think of a useful property to check?
We can maybe if we pass the token around our nodes.
Yeah.
Eventual termination that we eventually will detect termination.
Eventually detect termination. Yeah, that doesn't exist here, right? Termination detected. That's in the high-level spec. But something like this. We could probably just go to the previous specification and copy-paste some stuff into this one. And copy-paste works fine for specs because they are so small. But we said yesterday, right, that the left-hand side of this spec implies some property. Yesterday, I believe it was stable, and the other one was spec implies live. The left-hand side and the right-hand side are just formulas, right? So what we might want to do here is say that this spec here implements the high-level spec, and I will call it ATD. And let's say there is a namespace separator here, which is the bang. And I could state this theorem here and check it later with the model checker that spec implies the other spec. So in other words, the behaviors defined by spec are a subset of the behaviors defined by spec. That would be useful, right? Huh? And because we can both sides of this, TLA plus everything is a formula, this is easy to do. We just say that this program generates behaviors that are also behaviors of this other program. There is no program, right? But for figuratively speaking here. Obviously, this doesn't work here. There's some syntax error because this ATD here is nowhere defined. So what we could probably do is, what we could try to do is extend async termination detection. Unfortunately, this gives us countless name clashes, right? Because there have nodes in the async termination detection. We have the assume, we have the n, we have half of the variables in the high-level spec, and so on. And I said an extend is really just concatenating this other spec in front of ours. So this doesn't work. Okay, so there's a second mechanism in TLC to make use of another specification. And this is called an instance. So we instantiate async termination detection. And I turn it into a definition so that I get this thing as ATD. Okay, and this took care of this syntax error down here. But it unfortunately only moved the syntax error 2 lines up. So no success there. So what does it say here? Substitution missing for symbol termination detected declared at line so and so in module async termination detection. Okay, so we have a syntax error because there's some declaration missing. What's the declaration on line 63? Well, that's the variable here, termination detection, which we don't have in the low-level specification in EWD 998. That's a bummer. So we could probably just copy-paste this variable here and add it to the variables. And this makes our problem go away, at least the syntax problem here. This works now. So we could, and I'm going to change this now into something that the model checker config accepts. It doesn't, the model checker config doesn't like the bang, so I have to come up with a quick definition here, mccfg, and check the property ATD spec, right? Okay, let's see what happens.
I think you forgot to include this new variable to vars.
Okay, yeah, that's true. There's a different problem, right? It's not part of the vars, but it also, there's no definition of it, right? We would have to come up with values for termination detected in all the actions if it changed somewhere, right? But I don't really want to do that because termination detection, that's not a variable of the spec, that has no meaning and it doesn't appear in Dijkstra's writing as a variable. So it's really wrong. Instead, what we want to do is we want to substitute with, and there's this with keyword, we want to substitute termination detected with something else in the high-level specification. So for the behavior in a high-level specification, the variable termination detected will just be equal to true because of this statement. right? So we don't have to define the variable here in our spec and set its values in the action. We can just do the with statement here. Unfortunately, the true is a little bit too simple, right? Because now termination detection is true, but in the high-level spec, pending is 0, 0, 0, but active is false, false, true, right? That violates the behavior of the high-level spec if we just do true. Bummer. Problem, right? But we've already checked something, that our specification EWD998 doesn't implement ATD spec or the high-level spec. So we check that it doesn't implement it. This theorem so far is wrong. It's not a theorem. Let's see if false perhaps works. Excuse me. And this gives us, oh, temporal properties violated. Some stuttering. Okay, that's strange. And we would have to think about this a little bit more. The explanation why, I mean, it's a trace, and this is now the termination has been detected by the high-level specification. But, sorry, the termination has occurred at the high-level specification, but termination has not been detected because termination detected is always false, right? So we really have to define what it means for this specification to detect termination. And we would do, again, in other words, translate it into what it means to have a conclusive round, right? We stated an initiate token passing. We stated what it means to have an inconclusive round. Here we would state what it means to have a conclusive round. And because it's a little bit of typing, I'm going to once again move ahead with the commits. Here is what it means to have a conclusive round. So termination detected in the high-level spec is going to be substituted by what this evaluates to. Token is at position 0. The color is white. The sum of the token Q and the initiator's counter is 0. The color of the initiator is white. Everybody is inactive, and there are 0 pending messages. And now we can see, check that things work. It still doesn't work, but what's this now? Stuttering. Stuttering we've seen before, right? So this is once again this liveness thing we will talk about next. But for most parts, if we go to the safety part of the high-level spec, where is spec here? I have to find spec real quick. So here is spec. Let's say I remove the fairness part of this specification here and check this again. It says, oh, yeah, so the safety part of EWD 998 actually implements the safety part, already the safety part of the high-level spec. So the violation with the stuttering we saw was a violation of the fairness of the high-level specification, right? But really the point here is we refine the specification by some kind of refinement mapping. This is the refinement mapping here. And then we can check really if this low-level spec implements the high-level spec. So the high-level spec really becomes a property, and it is a property from the perspective of this spec here. It also means that you can essentially write very, very complex safety properties, but just writing a behavior spec. You don't just have to use the temporal formulas, the concise temporal formulas. You can just write a behavior spec and make it a property. Okay, let's see. I think there's one refactoring now going on here. Once again, just syntactic sugar. I refactored this termination detected into a definition that happens to have the same name as the variable in the high-level spec. And with that, I don't have to write the with statement here anymore. This with active, and so on, you don't have to type that. But this is, once again, just a bit of syntactic sugar. Okay, and now, obviously, unless there are questions up to this point, we probably want to take care of the fairness part. So let's see. In the high-level spec, unless I've broken it, spec, we have weak fairness next. So maybe let's add this here too. And see if it works. Weak fairness in the lower level specification perhaps also implies weak fairness on next in the higher level specification. That's not good enough. So we now get a lasso. Infinite cycle as a liveness violation. Initiate probe, send a message, pass a token, pass the token, initiate message, send a message, initiate probe, send a message, pass a token, and so on. So some send message action keeps getting into our way in terms of termination detection. Because this is what
please you could elaborate how you read this this trace.
Sure.
Because it's not quite clear.
Okay, sure. So we started in an initial state. We started in an initial state, then we get a trace, a regular trace up to state number 5. Now with some variables changing. This is no violation yet. But because there is this back to state here, and I think this 4 here, that's a bug. Because here it takes us to the initiate, and I can also, it's a bug of the VS Code extension. Let's look at the full output. It says in the text, it says back to state, initiate probe, line so and so, so and so. And for some reason, the VS Code extension pauses the thing.
I see. So we have infinite loop.
So we have an infinite loop from some initial state, then it goes to initiate probe, send message, pass token, loop back, initiate probe, send message, pass token. So remember three nodes that keep passing the token, but there's always a send message that means there's no global termination. So we keep passing the token over and over and over again, but some send message action gets in our way. And that's fine, right? Because from the perspective of Dijkstra's termination detection algorithm, it doesn't require that things terminate. It just detects termination if things terminate.
Sorry, but we have that constraint that we are not sending more than 3 times. Why doesn't it help?
Okay, right. But that's just a constraint of model checking, right? Logically, in terms of this liveness checking, this fortunately doesn't stop this counterexample from appearing. Because still the number can be incremented. Right? In the liveness checking algorithm, how the model checker works, it still detects that there's a cycle here of the counter going up and up and up, or up and down and up and down, up and down. Because the counter really doesn't have, the thing that's important is that the counter is not 0 for the messages being in flight, right?
This is what the liveness we send checking, and receive. We send and receive the message. I see. Oh.
There could also be receive here. In this particular case, it's just a send message. But fortunately, the model checker is clever enough to find this violation here. But yeah, it's a valid concern with state constraints and action constraints, and also with something called symmetry reduction, where you declare certain values to be symmetric. It's easy to shoot yourself in the foot, especially if you check liveness and miss counterexamples. Yeah, we want to constrain the state space, but if we constrain it too much, then we won't find violations of our properties. Okay. Getting back to fixing this liveness part, what I want to get at is that we've defined, where is it? Okay, we've defined fairness on the next state relation. So that means its system is fair or environment is fair, which means send message is fair or receive message is fair or deactivate is fair. So this enabled operator that sits inside of this weak fairness formula here, that doesn't distribute over the disjuncts of this action here. The operator doesn't distribute, right? It doesn't apply to all of the disjuncts, but only if one of the disjuncts in this next operator here is enabled, then this satisfies the weak fairness and also the strong fairness. And conceptually, we obviously don't want our termination detection to assert fairness on the environment doing something. Yeah? Dijkstra is not about the environment, the computation achieving progress. It's for a specification of the environment, of whatever the computation is to do. We just want to constrain our spec to fairness on the system. Okay, so does it solve our problem? Not yet done, because now we have just initiate probe and nothing happens. This is now actually something we have to correct here in the high-level specification, where we also, the same argument applies that I just made. We restrict the termination to the fairness to the detect termination formula, and assuming I made no mistakes. We now have ironed it out, sorted it out. We have fairness on the right actions and not on the actions that conceptually represent the environment.
I'm sorry, what did you just change in the higher level spec?
I changed the next. I removed the fairness on next to the fairness of detect termination.
I see. Mm-hmm.
So which is, if you think about it, the system and the lower level specification. Here in the high level spec, we don't have system and environment. Here we just have terminate, send message, wake up, and detect termination. Terminate, send message, wake up, they appear in the low level spec as the environment, slightly different names. And then the system is detect termination. And in this sense, conceptually, I just said the weak fairness is on detect termination, the high level spec, and on system in the low level spec. And this is what makes it right. Because now, if it's possible to detect termination, informally speaking here, we will eventually detect termination. If there is no termination, then we don't force termination, but we also don't force the system to continue. The environment to continue. Our fairness constraint previously forced the environment, the computation to keep going, if it's possible for the computation to keep going, and this should not be a concern of our termination detection specification. But this is a lot, and liveness is tricky. Liveness is subtle. It's difficult to get liveness wrong, not because TLA plus is ill-suited to handle liveness, but because liveness is just difficult. And this complexity of liveness shines through, and you really have to think about this sometimes. But really think about how much reasoning about liveness you do in your programming. I would say none whatsoever, probably. Just assume that the scheduler does the right thing and hope for the scheduler to do the right thing. Okay, so let's quickly go back to our overview here. So we're done with the refinement, essentially. I can skip those commits. And now we should sanity check the specification again, because as Andre said, why choose, why not existential quantification? And we can probably use the remaining few minutes, times 7 more minutes, great, to look at that. So we're done with liveness now. There's exercises, as I said, in the in the material. Let's see. Now let's take care of this choose here. Where's send message? Here's send message. And what I'm going to use again is the simulator that we've seen yesterday. I'm going to once again generate some 10,000 schedules, but this time one full statistics. Takes a few seconds and it's done, and this should be it. Let's close this guy. Arrangement here. Okay. Ooh, already a quite complex diagram. So yesterday we only saw the 5 actions. Now we see all the actions except for initiate probe 3 times, because now we see the value, the parameter of the action with which it's invoked, called executable. So this row here is the send message, receive message, and deactivate with I equals 1. Probably make this a little bit larger with I equal 1. This one here is send message, receive message, and deactivate with I 0. Initiate probe doesn't take a context, so this is why it only appears 1. Here's pass token for 2. Here's pass token for 1. And here for I2, we have the send message, the receive message, and the deactivate. And once again, we have these suspiciously looking green arrows that say receive message for I equal 2 doesn't happen. It doesn't occur. There's a problem, there's a bug in our specification. And you've seen TLA plus before, some of you, and are already suspicious of choose. So what happens here? So in this choose, we get the I equals 0, and I think choose will probably choose for J 1. For 0, it chooses 1. For 1, it chooses 0. And for node number 2, I guess it chooses either 0 or 1, right? And that means we never choose 2. So this is clearly wrong. Bummer. Looking at this action space visualization reveals these kinds of problems. And the advantage of these action space visualizations is that they don't grow linear with the state space, at least with the basic one where you don't pass in the context. But this constant, so it's independent. The number of actions is usually pretty low per specification, right? So it becomes feasible to generate these visualizations. But there's also another way to detect this that I'm going to show now. So what I do is I can set a breakpoint here and quickly open some other file, and perhaps we get interrupted by the break. Then we will continue with this after the break. And now I can click on this check and debug model with TLC. Let's get rid of the simulate here. And the debugger fires up. Let me just quickly make more room for the debugger. And now this is a new feature in TLC, and it's also pretty new in the VS Code extension. I just implemented the debugger a couple of months ago. It's still a work in progress, but it's already working. It's already useful. So the debugger is by default stops at the first instruction that TLC evaluates. So it evaluates the assume up here for our n. So n is 3, and now TLC checks if this assume actually holds or not. Great, but we're not so much interested in the assume. Let's resume, and now it hits the unchanged here. And I can inspect the variables, can see where we are in the trace. So this is now the send message step after an initial state. The behavior is just 2 states long. I can see the value of the variables. I can see the state being created. Some of the values haven't been assigned yet, right? Because we're before the evaluation of the unchanged. So active here is undefined, color is undefined, and token for the primed values are undefined, right? The old values we can look at here. Okay, and then we could step over it, and these values would probably show up in the environment. There's another kind of breakpoint. My mouse is a little bit broken. Use another mouse. Get the context menu. Okay. Add inline breakpoint. Can remove this guy here and resume. And now we get to see the successors of this action, that this action leads to. This set of successor states. So we are at a state where we're sending a message by some node 2, and it only causes one successor state, right? And what we actually want to model is that it results in many 2 successor states because we send messages to 1 and 0. And here we just happen to send, what is it? We send a message, the pending gets incremented for node number 0. So node number 2 only sends to node number 0, but never to node number 1. Okay, so that's the TLC debugger, and which offers another possibility to look at the to get some insights into the specification. It also has, what I find pretty neat, that add a hit count here, and then the action would only fire if there are at least 2 successor states. And there's hit count also for other expressions. And obviously, with a hit count of 2, this choose here will never, the breakpoint is inactive, right? So we want to rewrite this guy, and I have 1 minute left, so I guess I can do this in 1 minute. There exists an n in node that's perhaps not the I, such that.
Hello, Markus, and everyone who
Hello.
is looking. Yes, and we are interrupting for a small break.
Okay, that's fine.
Yes.
Continue after the break.
Thank you for showing us the debugger and the TLA+. It's very fascinating.
I assume